Today we are going to discuss the vector control of induction machine. Actually, many of the cases I have seen the students, they are unable to understand the concept properly, and myself also struggled a lot to get a clear idea about that concept. So I am trying to share my experience and knowledge about the vector control of induction machine. Basically, uh, the vector control of induction machine has been evolved from the concept of separately excited DC machine. Actually, the machine dynamics of an induction machine is quite complex in compared to a separately excited DC machine. But where you need a decoupled control, means the torque and the speed will be controlled in a decoupled manner, which means when you are changing the torque, your speed will be unaltered, and when you are changing your RPM or speed, your torque will be unaltered. This thing is called decoupled control. Now let us try to learn what is the equivalent circuit of a separately excited DC machine. So this is this one, and here this is your back EMF, this is the brushes, and this is your armature circuit. This is the armature, this is the armature inductance and armature resistance, and the current flowing through the armature is instantaneous IA, and here you are applying VA or VT something, and this is your field circuit. Here your field current is going, and here this is your field circuit. Now if you see the governing equations of a separately excited DC machine, the torque is given by some constant into the flux and the armature current, and the back EMF of the machine is given by EB is equal to another some constant into flux into omega. Omega means that is the RPM of the machine, means the angular speed of the machine. Now from here it is very much clear that if I want to change the torque of the machine, I can change the armature current by varying this VA. So in that case my flux is, I am not touching the flux, it is constant, means I can keep it constant by keeping this voltage as constant. So now if I change the armature current IA, my torque will be unaltered, but my torque will be changed, but my omega, speed of the machine, will be unaltered. And similarly, by changing the field, if I change this, my field will change, and that is required when I want to operate the machine in constant field or weakening mode or some elevated field, whatever is needed. So basically, for the torque control and the flux control in a separately excited DC machine, we are getting two electrically isolated circuitry, but the same thing is not possible for an induction machine. The total current which is drawn at a certain instant, you cannot predict from that amount of current how much is producing the torque of the machine and how much is producing the flux of the machine, because it's a vector summation, and that is entirely dependent on the instantaneous rotor position. Now to achieve the same analogy for an induction machine, you have to model it equivalent to a separately excited DC machine. Now let us see the governing equations governing equations of induction machines. First we will write down the voltage equation. So VSD, that is the direct axis stator voltage, which is rotor resistance, into ISD, means that is the direct axis stator current, plus rate of change of flux of psi SD minus omega s, which is the synchronous frequency, into psi SQ. Similarly, VSQ is equal to RS ISQ plus d dt of psi SQ minus omega s into psi SD. Similarly, for rotor direct axis voltage equation, this is the rotor resistance, into IRD plus d dt of psi RD minus omega s, sorry, this is plus, so minus omega s minus omega m. Omega m is the mechanical speed of the rotor, omega m into psi RQ, and V RQ is equal to RR into IRQ plus d dt of psi RQ plus omega s minus omega m into omega s minus omega m into psi RD. These are the four governing voltage equation of an induction machine. Okay, now we have to write down the flux equation of an induction machine. So that psi SD, which is equal to LS ISD plus LM IRD, and your psi SQ is equal to LS ISQ plus LM IRQ. This LM is the mutual inductance of the machine. And what is LSS? This LSS is leakage plus mutual. This is the total inductance of the machine, and that is given by this is the leakage part and that is the mutual part. Okay, so this is the thing. So similarly, for rotor, psi RD, which is equal to LR IRD plus LM ISD, and your psi RQ is equal to LR IRQ plus LM ISQ. So these are the flux equation of the machine.